Okay, we'll talk about the need of quantum mechanics. And the need of quantum mechanics came from several problems in classical physics, which we are not able to solve within classical physics, so we have to need quantum mechanics. The first problem is the black body radiation. Here you have the curve of the black body radiation. Black body radiation is radiation, thermal radiation, from a furnace at a given temperature in state of equilibrium. It means you keep the same temperature and you check inside the intensity of each frequency. This is the curve that you get. As the frequency is higher, the intensity goes higher, and it shifts the maximum. Now, classically, you can obtain the beginning of it. For very small values, it is fitting the curve perfectly. But it predicts ultraviolet catastrophe, that for high frequency, there would be very high intensity, that really, if this would happen, we would not be able to use a furnace. We would open the door, it would be blind by the X-rays coming out. But this doesn't happen. And the curves, instead of going to infinity, they go to zero. This was a very challenging problem for people until Planck came with the idea that really we are talking here emitting of energy photons from the walls of the furnace and being absorbed back. So it's like a balance equation. And the question is if you can be emitted or absorbing any frequency, any energy, then the original classical curves would be right. So Planck suggested that this is not the case, that the photon, energy of a photon can be only proportional to a given frequency, proportional to some constant times nu, or h bar omega. And assuming this assumption, you can easily show that the intensity of the curves should be as they are observed in practice. That means, and from this curve, he was able to find the value of h and h bar. The difference of them is 2 pi. Now, the assumption was arbitrary assumption, no reason for it, but since it fits so nice the curve, so it was assumed that probably that has to do something. And new laws of physics coming in. And then you have to remember this constant h and h bar occur all the places in quantum mechanics. And it's really, they exist only because of the curve fitting for this experimental curve. Later, the quantum mechanics was able to explain why it is so, that really we have here motion of a harmonic oscillator. A harmonic oscillator is the vibrations with around some point. We are talking about the atoms of the walls of the furnace, and they, when the temperature goes up, they start to oscillate, getting some energy. So we are talking about temperature is showing how much the size of the oscillation. And if those harmonic oscillators have an energy not continuous one, as we had in the classical one, you remember in the classical oscillator, we had also a given frequency. Each oscillator has a typical frequency of this oscillation. But we can change the energy by taking the higher amplitude or giving additional velocity at the beginning. And the energy was conserved, but it was depending on the initial condition. What we need to, was shown that this energy is proportional to this basic quanta, which is h bar omega, a constant and a natural number, and there is an initial energy which we denote E0, and we'll say what it is later.
Sorry, Yaakov, can I ask a question? Is it possible to ask a question?
Yes.
The curve, the black body radiation curve seems the graphs are continuous curves.
Right.
Whereas, you know, when you have this energy of the photon, you got this n. It seems to be is discrete. So
Well,
how
you obtain it? The way to obtain it, you have to use this process is a random process, and you use the theory of Markov chain, which tells you how to transition from one level to another. And then on this Markov chain, you can calculate the average energy, and then you get those very smooth curves. Really, it comes in, instead of only going exponential growth, it comes in and multiplied by a negative exponent. And that pushes everything to the zero. I have all those things worked out nicely in the textbook that I have written when I taught quantum mechanics, but it's only in Hebrew. It has all those things worked out with detail. Now the next experiment, which was even surprising for the founders of quantum mechanics, was Stern-Gerlach experiment. And here is the picture of this experiment. They start also with a furnace. They put their atoms of silver. Why silver? Silver has a unique thing. He has his structure of the atom. He has an extra atom outside, like, which makes a silver atom magnetic momentum. So it rotates around the atom. Since it's not balanced by other electrons and protons, and therefore it has a magnetic momentum. And so they want to check the size of this magnetic momentum. So how you check a momentum? You put it between two magnets, but you need to have the magnets of different shape. One is a wide one and one is peaked. That means it generates a magnetic field with changing strength in the direction of Z. And what they expected to get, like the usual curve when you get through a hole, like distribution, Gaussian distribution in the center. And instead of this, they got two spots, nothing in the center of the ray. Everybody was affected by the field either up, either down. And that was totally shock for the people even in quantum mechanics, because all the quantum mechanics, the earlier one, would not predict such things. They would predict a spread of the beam, but not having two spots. So the answer for this one is what we had in the lecture, I think number 8 or 7, when we talk about the field of electromagnetic field and we introduced the prepotential, we found out that the representation there is spin half. Spin half representation till that time was existing only a theoretical introduced by representation of the Lorentz group by, I think, Gelfand, but nobody thought that it is realized in reality. And then they found out this is an expression that it's not, the momentum is not represented by the regular representation when we have the angles and rotation is by regular rotation. It is rotation by the spin. And in the spin, you have plus or minus 1/2. And that's why it's called spin half. And there's nothing in the zero, and therefore we had an empty, no silver reached the central point. Then the next thing, which was very challenging, the hydrogen spectra series. Why we start with hydrogen? Hydrogen is the simplest atom, only one proton and one electron. So if you know to solve the problem for the hydrogen, basically this is the basis for solving, understanding all atomic levels. And when you look on this, you see different lines indicating there is the photons emitted from a hydrogen atom of a given frequency, of a set of frequencies. And Rydberg found a formula for them. The formula was a constant that he was able to define from these lines, 1/n1 squared minus 1/n m squared. Where n and m are two natural numbers. That means, once more, an indication that the energy level of the hydrogen atom are some constant times 1 over n squared. So since we see only the difference between two levels, so we see the difference with 1 over n squared minus 1 over n squared. So I want to explain you how those things are explained now by the quantum mechanical model. So to explain those things, they really changed all the physics, and we'll try to understand what it is. So first of all, we have to understand better the notion state of an object. We have seen in classical mechanics that the differential equations describing evolution are of second order. Second order equation, in order to define the trajectory, you have to have two initial conditions: the position of the object and its velocity. Those two things are called the state. State is enough information about the object. When we knowing the laws that with this initial condition, the state, you'll know what will happen in the future. Now, when we talk about quantum objects, we have to consider that they are not really points. They have some kind distribution around them, like some kind of fields around them. And those are not points. So we have to talk about distribution of their position and velocity. Here I draw you a picture that's from my book, and how it looks like a wave function of a particle. It looks like you have here like a complex plane, and then here you have done the picture for one-dimensional one. So in the direction x, we call it, we have to have a function which is a superposition of plane waves which generates together something localized within certain region in the space, and it has some kind of typical frequency. So what is the definition, the axiom, the first axiom of the state of a particle in quantum mechanics? State of a particle is given by the wave function, which is complex valued function on space. We are talking about non-relativistic quantum mechanics. Relativism, all those problems that we discussed are not solved yet. So you have place where to do. The non-relativistic considers time as a parameter as in classical mechanics. So we have a complex valued function. This is something similar in quantum mechanics. They don't give physical meaning of it. The whole meaning is the following: the absolute value of this function is the position of the particle's probability distribution. The absolute value should be normalized to be able to get the total integral to be 1 of this one, the square of this function. And why it must be complex, why shouldn't be to get this distribution, it's enough to have a real valued function or even positive value. But you remember from classical mechanics, you need to add information about the momentum. And if you take a real valued function, you'll get the distribution of the position, but where will be the momentum? So therefore, they made the function complex valued. And if you take the Fourier transform of this complex valued function and take its absolute value, you have to put absolute value squared to have the probability distribution of the momentum. So having the information about the position and having information about the momentum, you generate some kind artificially a complex valued function in such a way that the absolute value of square you have to put of the function itself is the probability distribution of the position, But for the Fourier transform is the probability distribution of the momentum. It's not easy to generate such function. In practice, you never get this from this information. You get from some kind of equation, but you came up always with a complex valued function. So the state space that you remember that people in Jordan algebra talk about state space. In the regular state space is those functions. They have to belong to L2 because we need to have that the integral of the square can be made that one. It's not a Hilbert space. Any book or textbooks will tell you it's a Hilbert space. They never complete it, and they don't want to complete it for physics because you want the dual space to be much larger, so that the functions like e in power I lambda x will belong to the dual space. In order that they belong to the dual space, those functions has to be very localized and very smooth.
Excuse me, why did they pick the momentum as the Fourier transform? Because of convolution?
There's no answer.
No, because
no answer.
Like, for example, convolution time domain is multiplication.
Right. When you have I'll tell you, when you get the solutions for harmonic oscillator and you get the absolute value of psi, and you see that as psi goes up, the energy goes up, the amplitude average goes up, and the velocity also goes up. So it is reasonable. Okay, it can be justified a little bit by considering what will happen if you take a wave packet and you let it to move. Look, if you're moving this wave packet in some direction, it will like start to rotate. And this rotation is somehow expressed in the Fourier transform when you decompose it by simple waves. So it's not fully justified, but that's the best justification that you can get. Now, what would they have done with the next problem, with the spin? So the spin, they represented a new space. The state of the spin is now another space, C2. I forgot to tell you, if you multiply this psi by a constant, complex constant, since the function is complex, it means you change the phase or you change the magnitude, it is presenting the same physical object. The state is like a projective plane in this space. So you really, why? Because anyway, you need to normalize to give the physical meaning of them. And multiplying by absolute even power lambda phi doesn't change the absolute value. And on the Fourier transform, it's also not changing the magnitude. So it is this assumption. When we talk about the spin magnetic momentum for particle, let's call it S, is represented it's by C2, a pair of complex numbers. Why complex numbers here? Here how you build it. You build a basis in this space. We take the result of the Stern-Gerlach experiment for the one that beam that went in the positive direction of this z-axis went up, you denoted the phase vector basis 1, 0. The second one is 0, 1. Why it has to be 0, 1? It's in the same direction, but not. They have to be perpendicular each to other in the sense that the inner product has to be 0 because they are exclusive. Exclusivity means in the inner product they are perpendicular. So to have something perpendicular to it has to be 1, 0, and you have already the two basis vectors. Nothing can be orthogonal to them because we don't have more beams that don't give you a component in the Stern-Gerlach. Something will give you some probability going up and some probability going down. It means all other ones are a combination of those. You take a beam in the x direction. Now, when you go at the beam in the x direction, it will, when you split it by the Stern-Gerlach in the z direction, it will give you 50% up, 50% down. So you need such a vector. You have 1 over square root of 2. The inner product will be 1 over square root of 2. Square of it, both with z1, z plus, and z minus will give you n. Now you have x minus. If you will go in the x direction, one will go in the positive side, and the other one will go into the negative. It has to also have the same probabilities here, and perpendicular to this, you still have such a vector, 1 minus 1, 1 over square root of 2. Now, but there is also a z direction. And you are run out of all the possibilities. The z direction needs to give once more half probability here and a half probability with this vector. And it has to be also have probability to x plus and x minus. So the only way to get there is change the numbers into complex numbers. Totally different reason. Since our space is three-dimensional and we can represent spin have only 2 dimensions. And the third dimension, we don't have room. We cannot add another dimension. So it has to be, and we have to add the dimension of the numbers to turn the numbers from real to complex. And then you are lucky, everything is good. And those are the 4 numbers, and everything is a combination of them. And you get the same thing. You had a space, 2-dimensional space, complex. And once more, multiplication by any number will keep the state the same. So you have to have a projective plane in C2. And then the representation is the one that we got pi L in our lecture. So this looks very close to the thing, to our model, because we were talking about the electromagnetic field, and we have seen that even classically, if you do it relativistically right, you get spin-half representation. So in general, this is the axiom, the first axiom in quantum mechanics, and the state space is a complex vector space with an inner product, and psi x is equivalent, and k times psi x for any complex number represent the same state. So that's, we described how the description is, and each problem it is quite different, but that's the general outline.
Is there a concept of velocity here also, or no?
Momentum.
No velocity, nothing.
No, they replace it by momentum. And I think it could be done, but it should be done. The next thing you have to define observables. Observables, what is an observable? It's a physical quantity that can be measured. That's the definition. For instance, position, coordinate of position of an object, coordinate of momentum, energy. Those are the 3 main things that we will need for today. Okay, the axiom tells you, very strange axiom, any observable is represented by a self-adjoint operator, basically you mean not self-adjoint, Hermitian operator, on the state space. We said that the state space is a complex space with an inner product. We can define which operator is Hermitian, and the set of Hermitian operator represents all physical quantity that could be measured. Why? Mostly when a mathematician came to this, he got the wrong impression that they are talking about an operator for us is a linear map, not for physicists. There's no meaning for this linear map. Don't try to get the meaning, it has no meaning. So let's see why they define this. They didn't look this consideration, but that's the way I am teaching students. let's look what properties should an observable satisfy. What kind of data it has coming with it. You have an observable, you know what are the possible outcomes of it. And in different with the classical one, we have to include also discrete values. So an observable can get continuous values, it can get discrete values. It can be finite or infinite. So you have a collection of observed values, which are real numbers. There's no meaning for the complex numbers. They are only a technique on the while we work. The outcomes should be real numbers. Next thing, you have to tell us when you have a physical measurement, your state changes. When you have a wave packet which was oriented in any direction, and you went it to Stern-Gerlach, it got a definite orientation. So any measurement, since the object is very small and the measuring devices are large with respect to him, so they change its state. So when if you observed each aj, there is a corresponding state, psi j, such that the outcome of the measurement was aj, when you measure this value a, the system will be in state psi j. That means you know after you measured and observed some value, what is the state corresponding to it. And another thing you have to be able to say, what is the probability to get this outcome. Those are three properties that an observable must satisfy. Now, a joint operator, what? Yes, question, please. You can ask. So, why they picked up to be a self-adjoint operator? So, any observable physical quantity which could be measured is represented by a self-adjoint operator. We put it at a hat on this state space, and how we connect with all this information. Any self-adjoint operator, the eigenvalues of a self-adjoint operator are real. So you need all eigenvalues are exactly the possible outcomes of the experiment, of the measurement. That's how the eigenvalues of A are exactly the possible outcome. Each eigenvalue has an eigenvector. The eigenvector is a state corresponding to this eigenvalue. Now, a very important property for these states, they have to be perpendicular each to other. Why? Because if you measure the value A, for instance, you get the spin up, is definitely not minus. It means they are perpendicular in sense of the inner product. It means you need another property that eigenvectors corresponding to different eigenvalues are perpendicular. And that's also one of the properties of self-adjoint operator.
Operator, yeah.
So that's exactly defines you why you need a self-adjoint operator. And what will be, the eigenvalue will be, so you'll know the eigenvector corresponds, you know the answer B. And what will be the probability to get this measurement. So you look the initial state, inner product with the state after the measurement, and taking the absolute value squared. Since the psi was of norm 1, and you decompose it by vectors on orthogonal basis of norm 1, so the sum of squares gives you 1, so they can give them the meaning of probability. So in this way, a self-adjoint operator is a good candidate to keep all the information needed for a physical quantity which could be measured.
So in this quantum mechanics, you cannot measure an outcome exactly.
No, you could. You measure it. After you measure it, you're in a state that you can measure it exactly. You measure the spin in the z plus direction, and if you repeat the measurement, you'll still be in z plus direction. But you cannot, if you measure another direction, it will destroy this measurement. If you measure in the x direction, you lose this information. That's a very important issue. That's non-commutativity. Is a result of non-commutativity. When you perform one measurement after the other, you lose the information about the previous measurement. But that's exactly when you work with the operators. And there's not, it's the difference between the commutative and non-commutative case. In commutative case, if you add 1 point, you multiply by any function, you're still at the same point. Not so with operators. Okay, that's justification why they picked up this model. Now, where comes in the sister algebra? The sister algebra, well, operators on a Hilbert space, so they thought we are talking about the observables form a sister algebra, not the product, associative product loses self-adjointness. So then they invented Jordan algebra. When you have two self-adjoint operators, the Jordan product is still self-adjoint, and it was a big articles about this, but you have to know that the Jordan product has no physical meaning. The triple product do have. If you take an observable and another observable, and you consider ABA, it has physical meaning, but not AB Jordan product plus BA. So it's very questionable if one's Jordan algebra will be helpful to quantum mechanics. By the way, there's no justification why we must have this other structure, which has coming with Jordan structure. On the other hand, I like the operator on a triple, the D operator, DAA, like acting on any B, the triple product AAB, has all the properties needed. And it picks up the half that we need in most cases automatically by the Pierce decomposition. So I think the JB triples are more fitted, but it should be done. There are a set of papers of me with Bernie when we try to show that the state space has more geometry related to quantum mechanics, but there's still what to do. Today I'm representing only the usual approach. Okay, we will need for today two operators. One is the coordinate x of position. This operator on x on the function psi is x times psi. Psi is a function of x, y, z, and it is multiplying the function by x. Well-defined function. Such an operator is Hermitian, while x is real, so there's continuous spectrum. Now, when we want to define the momentum, definition of momentum is differentiation in the direction of x for the x coordinate. This can be obtained easily if you consider motion and the generator of it is the derivative. You have a problem that differentiation by itself is not self-adjoint. The adjoint of a differentiation is minus the derivative. In order to make it self-adjoint, you have to multiply by I. They use division by I, which is the same. And they brought in the constant h bar to make the units right. That's only for unit purposes. Really, the momentum has to do with differentiation in the direction of x, but multiplied by I. Those are the two operators which we'll need for today. And with them, we'll be able to explain all the two main problems which are solved in quantum mechanics, the harmonic oscillator and hydrogen atom. And in general, if you know to solve these two problems, basically you have the theory done. Because all the other things are built around these things. So that's the big challenge. Let's start with the quantum harmonic oscillator. So the idea is, in quantum mechanics, as follows. It's called quantization. You look the same problem classically, replace all the things all the observables from functions to be an operator, and then you obtain the quantum equation. So harmonic oscillator we have done in lecture number 2 has the energy of this way, the kinetic energy, and the potential energy is kx squared over 2. It's enough to solve for harmonic oscillator since it has a very simple potential. It reduces to the one-dimensional. So if you know the one-dimensional, you solve the problem. Now we want to not to use V as Professor Steiner suggests that we'll use V, but now in quantum mechanics we use P, which is mv. So you can write it P squared, which is m squared V squared. You have an extra m, you divide by 2m plus kx squared. Now we are in an expression which involves the operator P. We know how to represent it, and we know to represent coordinate x. So we write it the quantization of it. P squared, it has an h bar on the top, so it will be h bar squared. We had an I squared is minus 1, is the minus 2m we have here. And we had differentiation, but now we'll have to differentiate twice, is the second derivative. So this term, plus half k, this is a multiplication operator, so we multiply it by x squared over 2 psi, and it is equal, the energy operator has its eigenvalue E times psi, because on each eigenvalue, that's what's called steady state equation of harmonic oscillator. Why steady state? It's assumed that any state which is the eigenvector for the energy operator is steady. Those are all the levels, steady levels in a quantum system. Levels with constant, with definite value for energy. And the transitions are between different energy levels. Now we need to have that it will be an L2 thing, so the integral of psi square must be finite. Now this condition is some kind boundary condition. We know from partial differential equation, when we have a wave equation and we have boundary condition zeros, you get discrete values for frequencies, which in quantum mechanics could be described as discrete values of energy, because the frequency is related with energy. So here we don't have a boundary. The boundary is at infinity, but there's a trick how to solve it. And here are all the steps how to solve it. So first of all, you divide by this expression to get psi double dot. You get two constant, one x squared psi, and you took this on the other side, and we multiplied by minus, so everything became like we see. We call this expression here alpha squared, and the other one we call lambda. So we got this equation. Nice equation, second order differential equation. Only one problem, we have a non-constant coefficient. How you solve it? Okay, we do another simplification. We introduce a substitution y equals square root of alpha x. It looks like a good substitution will be alpha x, but not when you need here also the inner one. So we have the square root of alpha x, y differential will give you an alpha, and here an alpha, you divide by it, and you'll get this equation. Now, this is called Hermite equation. It has a solution, but what we want to have, we want to be able somehow to get estimate on this. So what you do in physics, you look on the behavior when y is getting large. So you can ignore this term, and you get that the second derivative is equal to y squared psi of y. Which function is doing it? Approximately is this function, e in power minus y squared over 2. When you differentiate, you'll get the first derivative will give minus y times this function. The second derivative will have an additional term, but you'll get one term will be y squared. This will be the dominant term. So this is an approximate solution. So we are looking for psi of y this function times f of y. There's no, can always write one function as another one times a function which is not never zero. But this function has already a nice integral of the whole r, a finite integral. So f of y, if it will be not growing widely, then you'll have the condition. So you substitute this equation here, and you get this differential equation. Nice differential equation, second order differential equation. This is a constant, but you have one non-constant coefficient, this step. Okay, how you solve such differential equations when you have non-constant coefficients? You write the function as a power series, and you get recursive relations for the coefficients an. You observe when this recursive relation gives you an infinite series, the infinite series is approximately e in power y squared, which is not good because e in power y squared will cancel this one and you'll get divergence and you'll not be able to satisfy the boundary condition. The only way is to get a final solution that satisfies this equation, that in the recursive relation, at some point it became zero. That means the solution will be a polynomial. And polynomial solutions are called those Hermite polynomials in this case. And it happens only in such case, where 2n minus lambda over alpha plus 1, which is this coefficient plus 1, equals 0. So you got, and since lambda is connected with the energy and h bar, and you substitute the alpha here, and you get a 1 h bar is cancelled, and you get another coefficient, and you get an expression for the energy. This is the expression for the energy. Harmonic oscillator, quantum harmonic oscillator, has the energy En equals n plus a half. You see here you have to divide by 2 to get n plus a half, and times omega 0, and the omega 0 is the known one that came from the classical harmonic oscillator, the frequency of the classical harmonic oscillator. We got exactly what we wanted because we have the energies are far apart one from other by the value h bar omega 0, and the omega 0 will be exactly the energy of the photon which will be emitted, and an integer times this value. It means all the energy levels are separated by some given constant term and times any integer number. So this solves the black body radiation problem and justifies Planck's assumption. Very nice solution for such thing. And what it uses simply quantize the classical equation, solve it, and find the solution which satisfies this boundary condition. Basically, it's enough to check that they are zero at infinity. Now we go to the next model. This model is even more complicated. It is the hydrogen atom. Hydrogen atom describe you the behavior of a electron in the hydrogen atom, which has only one proton. That means you have an electric field generated by the proton. Proton is much more heavier, and therefore we can assume it is at rest. And you want to define it's like planetary motion. The problem that we had with planetary motion, under the same potential, the potential energy is 1 over r, as we had for electric field. And this is the kinetic energy. The kinetic energy, as we have seen, for harmonic oscillator is p squared over 2 mu. But now the problem is three-dimensional. You must use the three-dimensional one. Now it's not, you cannot reduce to two-dimensional, one-dimensional as we had the previous time. At least you need 2 dimensions, but in general it's 3-dimensional. So p squared now will become minus h bar squared because we had an h bar there for p over 2 mu. Mu is now the mass of the electron, reduced mass of the electron. And you'll have the Laplacian instead of the second derivative of psi, Laplacian of the wave function. The potential energy gamma over r is multiplying the psi and equals psi. The whole difference is this potential energy became now 1 over r, and the problem will become three-dimensional. Now it is because it has spherical symmetry, you can look at the composition of it into the product, one function depending on r, and the other one depending on phi and theta. Now, using separation of variables, as we use for solving partial differential equation, you see that the equation for y is the same equation for Laplace equation, because the potential depends only on r. So it doesn't contribute nothing to the angular behavior. And this was an all solved problem, how to solve the Laplacian in spherical coordinates. And the solution for the angular part are called Legendre functions, and it's called spherical harmonics, y and l. They depend on two parameters, discrete parameters, m and l. M defines you the dependence on phi, e in power I m phi, and theta defines you the L. So we have known function, and when you substitute in the Laplacian, they give you the following expression, L times L plus 1. It is independent on the m parameter, and substitute the radial part of the Laplacian in spherical coordinate. It has expressions r times r, capital R, double prime, and you have an expression which involves this one came from the y, L times L1 over r squared. Then you have an expression coming from the potential energy, gamma over r, and the E, we took it on the other side, times r, and that's equals 0. Okay, so you do the first things, you see it depends not on r times r. Call it u. The normalization is really the normalization for u, because when you in spherical coordinates you have to rdr you have to take, and therefore you have this one. Denote those coefficients that you have here by k squared, another one, introduce another row as we have done the previous time. This reduces to such equation. So you have u of rho double prime minus, you have some constant times rho square, another constant times rho. This constant is mostly denoted by lambda, as we had earlier. But you have a free constant, which is 1 over 4, unit free. With this rho, with this substitution, you made this equation unit free. As we have seen in the last lectures, having unit free quantities helps you very much, because then you can apply any functions on it. Now what we do the same thing as we have done earlier. We look what happens when rho gets large. And gets large, we can ignore those two terms, and you have u rho double prime equals negative 1/4 u rho, and this gives you the solution e in power minus rho over 2. And look for a solution e in power minus rho over 2 times g of r. And once more, you get the equation for g of r, a more complicated equation. This is the Laguerre equation. And for Laguerre equation, you solve it once more by power series expansion. It is a singular equation, so you have a generalized power series. And once more, if you have infinite series, it doesn't converge, only when you have a polynomial for g of r, and this polynomial is called the Laguerre polynomial. And from this polynomial, you get that the energy is exactly gamma square mu over 2h squared times 1 over n squared. Now, this constant was exactly the numerical value for the Rydberg's constant that was known from analysis of the spectral curves of the lines. And that was defined empirically, and this model justified the whole quantum mechanics. Because if you know the hydrogen atom, you can from it get the structure of all atoms. Because all atoms are really increasing only the number of protons and neutrons in them, and then the electrons fill up the orbits for different L and N, and you count how many orbits you have on the phase level, and you get that there are only two possibilities. You have hydrogen and helium, and then you must go to the next level, and this way you build up the whole table of elements. This is a very powerful tool, and you see what is needed. What is needed is the main idea was turning this classical one problem into a differential operators, and using that you have this restriction of boundary condition, and you came up. There's a lot of technicalities how to solve them, but everything is straightforward by using hard work calculations. And you get this level, the energy level, which we want. Okay, that is the end of the new material. And I want now to go overview of the things that we have done here and to pose problems for future research. We started our lectures when outlining the general picture of physics, and you see that the basis principle, symmetry relying behind most of laws of physics are the principle of relativity. This is the fundamental symmetry behind both classical and relativity physics. What the principle states, the laws of physics are the same in all inertial frames. There is no preferred inertial frame. Now, the laws of inertia imply that the space-time transformation between inertial frames are linear. So you have to define those linear transformations. They know from the same principle that this transformation depends only on the relative motion between the frames, which is the velocity. Then we have shown that mathematically there are two possibilities, either Galilean transformation or Lorentz transformation. And here the physics splits into two regions. The first one is when we assume Galilean transformation, and we get classical physics, Newtonian dynamics. Why? Because in the dot transformation, time is absolute. Velocity addition is simply vector addition. Acceleration is the same in all systems, so the laws of physics, since they have to be the same in all systems, have to deal with acceleration. Second, Newton's law defines acceleration for moving object caused by a force, and it's assumed to be independent on the velocity of the object. We got conservation of energy, conservation of angular momentum. We were able to describe motion of planets, which was almost perfect. Binary stars. It works perfectly on the distances on the Earth if you don't need very high accuracy, or the things are not changing very fast. We have seen that, for instance, on the atomic level, things change very, very fast. So you cannot apply those things. You cannot apply it in cosmology, where the distances are very large, and you cannot assume that ignore the propagation of the field. The assumption was here that fields propagate with infinite speed, that really we don't need to introduce a field. We can define the force if you look on the position of the object and the position of the source, and you get the force. Now, what were the shortcomings? I mentioned a few of them. the laws of electricity, they are not invariant under those transformations, because a moving charge, which had a charge had only electric field, a moving charge has a magnetic field, which cannot be under Newton, no reason for it. Any moving thing and the rest have the same acceleration. Michelson-Morley experiment, it showed us that the velocity addition is not wrong. If you have a source is moving, the velocity of light of the moving source is the same as of at rest, while in classical velocity addition will change it. Fizeau experiment, the motion of light in water, when the water is moving, doesn't add up by vector addition, totally different addition. Precession of Mercury. All the planets in the solar system are making perfect ellipse, as we obtained here for the planar motion, but the Mercury is slightly changing its direction of the ellipse, which is called precession of Mercury. Very small, but it is not zero. Black body radiation and others, all those things are an indication that if you want to have more accurate physics, something is here wrong in the assumption. Another thing would, my point is an indication. We want to have the physical laws based on some kind optimum, variational principle. You can't get a variational principle, but the Lagrangian for the physical, for classical one has no physical meaning. So it doesn't look right. So we see that but there is another option to express the same relativity principle, and that's using Lorentz transformation. So we look what happens here. When we get the Lorentz transformation, we get new behavior. There is an invariant speed for all inertial systems, which was experimentally shown to be the speed of light. We got more even, we got an invariant metric. That means between events, and when you talk about the principle of relativity, it's talking about system moving one with respect to others, so you have to talk about events only. You can define a distance between two events, and this is invariant between all the inertial observer. We measure the same invariant metric, distance. The metric is called the Minkowski metric. It is not positive definite. So we'll have to enlarge our understanding of metrics and distances to also not positive one. This gives you right away a new velocity addition, not as simple as vector addition. And it resolves some shortcomings, Michelson-Morley, Fizeau experiment, and some others. So it looks like much better than the previous one. We get now the bounded symmetric domain, admissible velocities form a bounded symmetric domain under the affine transformations. The same domain can became under formal transformation if we introduce symmetric velocity between two moving objects. When we look at the automorphism group, we can represent it by a linear map on the acting on the manifold U, representing this domain. Each velocity you assign a 4 velocity, you get a manifold for the three-dimensional manifold, unbounded one, but all the geometry from here is translated here, but here the transformations are linear, so it's easier to work with them. The generators of this automorphism, the Lie algebra, became now antisymmetric tensors, and this is the reason why the antisymmetric tensors play the main role in the dynamics in electromagnetic. So how we have to change the dynamics. The relativity meaning replacing the Galilean transformation with the Lorentz tells us the acceleration must depend also on the forward velocity, because the forward velocity or the velocity are now non-trivial, they have a boundary. So you cannot have constant acceleration. So there must be a dependence on the velocity. That means the assumption, Newtonian assumption, that is the acceleration is not depending on the velocity is now valid more. Why it was not observed earlier? Because the dependence is v over c square, which is c is when there is very big number for most velocities. So v over c is a small number and square is even smaller. And therefore, we were able to live for a long time thinking that it is independent. To exist, this theory extends also to massless particles. That means in Newtonian dynamics, only we could describe motion of objects with non-zero mass. Zero mass could not be treated. Here we get also massless particle, but all massless particles must move with the speed of light. This follows almost from the definition of momentum and energy. In order that they have non-zero momentum and energy, they must move with the speed of light. That means fields. Fields are generated by massless particles. So therefore, they propagate with the speed of light. And it was proven experimentally that this is the situation. That means now we have a new additional information about the field. They are not propagating instantaneously, but they propagate with this universal speed, the speed of light. Now motion, how we solve now the dynamics. The dynamics now has to be split into two parts. I cannot write one dynamic equation as it was given in Newton's theory, F equals ma, because I don't know what is the force at this point. The force is changing with the position and time. So we do motion under force acting at a distance is described in two steps. First of all, you describe the field at any space-time point from the information on the source of the field. After you solve the problem for the force, then the acceleration of the object is can be generated by the field at this point. So you need the dynamic equation can be solved only after you solve the equation for the field. And we have done it for the two important fields, the electromagnetic and the gravitational one. We found the dependence is relatively simple. For electromagnetic field, the dependence is on the forward velocity is linear. And for the gravitational field is quadratic, as we have seen one in the theory of bounded symmetric domain. Those are the two typical maps for generating. And that's what happens in physics. Now for electromagnetic, we assume that we have linear dependence. And assuming that the field propagates the speed of light, we were able to describe the field. There exists a prepotential of a field, a complex valued function of space-time similar to the wave function in quantum mechanics, but it is already on space-time, and it has an invariant under the representation, so it has much more structure. The gradient of the prepotential after conjugation is the complexification of the four potential known for the electromagnetic field. We even don't have to assume Newtonian limit, only general considerations. The prepotential is invariant under spin-off representation of the Lorentz group, similar as we have seen in quantum. When you consider the field, you have to differentiate once more. The four potential is one form. When you differentiate one form, you use the curl, and you get antisymmetric tensor as exactly needed to get the acceleration described in the electromagnetic field. What we get, this antisymmetric tensor, has different dependencies on R, on the distance. One dependency is like 1 over R, and the other one is 1 over R squared. 1 over R squared is called the near field, and the other one is the radiation field. It means there is a field propagating by itself when you have acceleration of the source. So that gives us the main ingredients of electromagnetism, antennas, and propagation of electromagnetic signals, etc. We looked also gravity. In gravity, we assume that the motion is by geodesic with respect to some metric defined by the field. This I use the general principle of inertia, that really all objects cannot move, change their velocity, so they have to go some kind uniform motion. And uniform motion in a curved space-time is geodesic. Now, the curved space-time must be defined by a metric, but if you define it by a metric, that fits very nicely for gravity. And you can easily define the metric. You assume that the field propagates the speed of light. And here we had assumed so far the Newtonian limit, but maybe at some point we'll be able to meet this condition. And this gives us the metric for a gravitational field of a static spherical symmetric body. We obtained this metric, and now we are able to describe the dynamics. What was interesting that we obtained, the acceleration is quadratic in the form velocity, as I mentioned, the other possibility that we had. We don't know to prove that there are only two possibilities, but in practice, there are only two fields that on non-atomic level that we know. The equations of evolution describe planetary motion, accurately predict the precession of Mercury. We couldn't use the previous one, the linear dependence, because it gives you only 1/6 of the observed precession. So gravity must use the quadratic one. It gives you the right formula of gravitational lensing. You can obtain Shapiro time delay. So the basic tests of gravity are passed here and obtained very short way. I was able to give it in one lecture. And generally, to give in the GR model, you need at least one semester. Okay, let's go now to open problems for future research. Okay, I looked over a few problems that can be formulated easily. We can study the symmetries of this manifold U of 4 velocities as a symmetric manifold. Maybe we can enlarge the automorphism group of U to describe also gravitational field, to have this additional electromagnetic field. To the electromagnetic field is described there because the linear maps are exactly describing the electromagnetic field. But I would like to have also the gravitational field, the quadratic one. Can we enlarge the symmetry and what we needed to be added, what kind of transformation to make it symmetric with respect to this transformation, that the quadratic one will produce the gravitational field. If this could be done, this would be very nice, showing that really those two fields are the only one. As you have the theorem for the degenerators of the automorphism group on a bounded symmetric domain cannot be higher than other two. That would be a very nice application. I want to get better understanding the complexification. And I have for you a hint how to get to this. There is another problem which we solved almost in general relativity. It's called the Kerr metric. Kerr metric is a metric of a gravitational field of a rotating spherical symmetric body. How it was obtained? It was obtained in the same way as I showed you in the lecture on gravitation the last time. When you reach to some form of the metric, and depending only on one unknown function f of r. And you have for this function, it has to be connected from the potential to the gravitational potential, the classical one, Rs over r, very nicely. So what Kerr has done, he said, if I have rotation, let's say about the z-axis, so I want to replace the z variable to become complex. Why? No reason. And he calculated what kind of metric he obtained, proved it satisfies Einstein's field equation, and this became the solution, and they see that it has some kind of behavior similar to a rotating field, rotation from a rotating source. And that's called the Kerr metric. So there's an indication that complexification really brings in the rotation. As I told you also in the last lecture, that probably because any state of an object can be measured by linear acceleration, but also rotational acceleration. So probably this rotational one is needed for complexification. And not as you got it for the quantum mechanics, you see, artificially brought in those numbers, either by missing momentum, either by missing dimension, the third dimension to put in. Okay, so can this help to understand the complexification of the space-time used in the lecture? 7. What is the symmetry structure of the complexified Minkowski space? We had the representation. It would be nice to see, can this be turned into automorphism group of some domain. Has to be defined what kind of transformation we do then. I guess maybe we'll get the first time then this complexified space, the analyticity. We have seen for the symmetric velocity, we are getting analytic maps. Maybe also here we'll get the analytic maps there, but people, not too many people know to work with analytic maps when it's on a manifold. And I think the bounded symmetric domain work with them quite effectively. This is an interesting problem, how to solve the relativistic dynamics of a binary star. We are missing now the center of symmetry, which was used for in the second lecture to solve this problem. Because really, we are missing one step in the general approach to dynamics. The dynamics was well defined when we know the position of the sources within the time. But if your object influences also the sources, then the whole structure is not fitted. So we don't have a real mathematics how to treat problem dynamics when the source of the field and the moving objects are influencing each other. And when you have a binary star, that is exactly the case. If any information could be added here, it will be a big help. People know that this is a problem, and maybe it will be helpful, the new coordinate that we introduced, which simplify this light cone, make it more nicer to become a plane. Maybe then you can solve this. We need to have soliton solution. It means solutions that will be able to be localized, as we got in quantum mechanics. This in power minus x squared times a polynomial. Can we get such solution for this prepotential? This prepotential gives us Maxwell equations. And there's a third order equation. If we can find, those are good candidates for representing those structures in quantum mechanics. Now, another thing is, this is a relatively not complicated one, derived Dirac equation from the prepotential. Dirac equation is the relativistic dynamic equation for quantum particles. It uses something similar of the gradient of our prepotential. And the matrices, Dirac matrices occurred there also, but I didn't finalize it till the end to show the connection of the Dirac equation with the prepotential. For them, the Dirac matrices and the psi are fully artificial. They obtained only to satisfy some conditions, and artificial they obtained. Here it became much more physical meaning for them. And the two problems that we solve today, quantum way, can we do it something by using the prepotential? Can we get harmonic oscillator, getting the discrete level and levels for our energy for the prepotential in a spherical symmetric field? Those are the big problems that will give us to get into the quantum region. That's all. With this, we finished our lecture for today. And let's maybe take a break for a minute or two to take the beverage to you, and I'll stop the recording and then we'll continue.
Thank you. Thank you, and thank you, and bye-bye.